Yes. Turn it on. This was the one from here, right? The other way around. Yes. A little button here in the top.
Okay. Hello?
Yes, it's good.
Okay, it's good.
So our next speaker is Srivatsan from Stanford, who's going to talk about optimal flexible consensus and its applications to Ethereum.
Okay. Yeah, this is joint work with my colleague Joachim, my advisor David, and our collaborator Lei from MIT.
Somebody from Stanford.
Yeah, I think if we just lower that, it's good now. It's good now, right? But it's still audible. Okay. Okay, so what is this flexible problem? So most of the classical protocols we see, like Hotstuff, Streamlit, all these SMR protocols, they are secure up to 1/3 adversary, right? And today in this heterogeneous workshop, we are basically talking about different kinds of users in the system having different beliefs, right? And so one such variation is like we have different kinds of applications running on the on blockchains, and each of these have like sort of different trade-offs that they want. So for example, you can think that Alice is maybe operating an exchange, whichever is your favorite exchange. And then this exchange receives a deposit of, let's say, 5,000 ETH, and there's a request to exchange this for 10 million US dollars on the exchange. Now, given the high value of this transaction, Alice might want sort of higher safety for this transaction, right? Given the high value, Alice wants that this transaction should never get double spent. So Alice thinks, better increase the safety even beyond 1/3. That would be great. So this Alice is like a safety favoring client. But if Alice wants to increase safety beyond 1/3, we know this is not. This has to come at some trade-off, and it comes at the trade-off of liveness. So Alice may be fine with this because it's a high-value transaction. She can wait to confirm it, but wants to make sure safety is there. But Bob, on the other hand, might be of the opinion that safety and liveness both matter sort of equally. And so Bob is like the liveness preserving client. And Bob wants both safety and liveness up to 1/3 adversary, not compromising on either of them. Right, so essentially, this is the problem. We want to design a protocol that can satisfy both Alice and Bob's requirement, a single protocol that can do that. And with that sort of motivation, I'll get into like the more formal description of the problem, right? So we have replicas running a protocol, and then we have clients. So the role of the replicas is that they receive these transactions as inputs. They run some interactive protocol, Pi. They send some messages back to the clients, and now the client, each of them reports a log or a sequence of transactions. Okay, yeah, of course, F fraction of the replicas are adversary, like Byzantine nodes. And now in this flexible formulation, each client comes with sort of a liveness resilience and safety resilience, a pair of two numbers. So Alice has one such pair, and Bob has one such pair. And the flexible consensus is defined for the set of all these pairs of all clients. And there are two properties, right? Liveness and safety. In general, we talk about SMR, these two properties. And now you want these to hold for the specific resilience. Sorry. So liveness means for all honest transactions, like correct transactions, eventually all clients that have correct liveness resilience, so the fraction of corrupted parties is less than their liveness resilience, these guys will output the transaction in their log. And safety means that for all clients K prime who have correct safety resiliences, so F is less than their respective safety resiliences, these guys will have safety. So these guys will have consistent logs. And so basically, it's allowing different parties to choose whether safety is more important or they want both. Right, so you can think of right away, like classical consensus protocols is like a special case where Alice, Bob, and every other client choose to have both safety and liveness resilience of 1/3. or 33%, right? And flexible consensus, now the idea is to give you freedom that maybe Bob stays at the point where liveness and safety of 1/3, but Alice says, I want safety up to 80% adversary and correspondingly maybe liveness of only up to 10% adversary. And notice that there are really two things happening here. One is each client is trading off safety and liveness, and that the different clients can do this in a different manner. I will pause here for a bit just to make sure that the problem formulation here is clear. And if you want, you can ask questions about the problem if that's there.
How would you replace what the 80% safety mean for Alice?
80 so safety resilience means that Alice and any other client also who chooses this 80% safety resilience, these two clients will have consistent logs as long as the fraction of adversary is less than 80%. So not 1/3, but up to 80%.
But then they tolerate less than the default 1/3.
No, 80 is more, right? So their safety resilience is more, but maybe Alice is not live in the sense that Alice's log doesn't grow, right? Okay. So then I'll continue with the presentation, and rest of the questions we can maybe take at the end. So yeah, all of this is in the partially synchronous network, which people here are familiar. And within this, the question we ask is, what is this maximum set of resiliences that a protocol can provide for all clients, right? And so let's look at that. Like, as you mentioned, there is some kind of trade-off between safety and liveness. So we can look at the safety resilience and the liveness resilience on two axes. So standard protocols we know provide sort of 1/3 safety and liveness for all clients. So that's this point here. And these are like Hot Stuff, Streamlit, Tendermint, Casper, many such protocols. And so this is nice for Bob, the client that I mentioned before, but Alice is not so happy with this. She wanted more safety. Right? So this is not flexible in the sense that all clients have to be here. One is happy, the other is sad. Now we know classic impossibility results that you cannot have both safety and liveness resiliences be very high. Right? In particular, if the resiliences satisfy this inequality 2TL plus TS greater than or equal to 1, then this is impossible. And so given that, you can now imagine that 1/3 is sort of the maximum resilience you can get for both safety and liveness, right? That's the point that we start out in classical protocols. Now, at the same time, when we start trading off safety and liveness, right, one might make this observation that liveness without safety is not that practically useful because, one doesn't really have a use for a log that keeps growing, but there is no safety guarantee, right? So in that sense, now the question is really, can we increase safety? Some clients may want to increase safety, but at the cost of liveness. And so that leaves us with this sort of white region here, where different clients may have preferences, right? And so that's where a previous line of work with like flexible Byzantine fault tolerance and strengthened fault tolerance from Dalia Malki, Kartik Nayak, Lindgren. These works explored this sort of problem where different clients can choose these trade-offs. And their protocol is basically you have a base protocol that runs with a 2/3 quorum, and it allows clients to choose to wait for a larger quorum before confirming transactions. And this achieves a certain trade-off between the safety and liveness resilience. So in particular, you can each client can tune its confirmation quorum, and it gets a different point here. So, okay, what happens then? Okay, Bob is still there at his point of 1/3 safety and liveness resilience. Alice is able to trade off liveness completely, and she gets safety up to a 2/3 adversary now, which is an improvement. But Alice is like, okay, happy, because maybe she wanted even more safety, more than 2/3. So there is some flexibility, yes. But now, if you want to satisfy Alice's high safety, you can try to do that with this protocol. I said that the base protocol had a 2/3 quorum, but maybe you can increase that also, right? So the base protocol now runs with, let's say, 4/5 quorum, and each client can choose even more quorum than that. And so now everybody's safety increases, but also everybody's liveness decreases, right? So now Alice is very happy, but Bob is not happy again. So basically that leaves us with a question that there's in both these green plots I showed, there's a portion of this white segment that's left empty. And so the question is, can a protocol support any set of resiliences for which you have this 2TL plus TS less than 1, so it's below the red region, and also it's more safety favoring than liveness, right? And our answer to this is that yes, we have this set of optimal flexibility or OFlex protocols, where we have the same two ideas as before, where you run a base protocol with 2/3 quorum, and then you have client-specific confirmation quorums. But then we add another tool to this, which is like one thing we call a permanent lock and another round of voting, which I'll explain soon. And with this, we can basically achieve optimal safety liveness trade-off for every single client. So both clients are happy. And so this question turns into a theorem, which we prove that, yes, you can achieve all pairs of resilience which satisfy these two inequalities. Okay, so with that explained, I will get into the construction. And so what I will explain now is I'll start with classical PBFT consensus. As an example, I'll take stream-led, but everything I'll do from now, it applies equally to like Hotstuff, Tendermint, or Casper FFG in Ethereum. I'll briefly go over the FBFT, flexible BFT construction as applied to stream-led, and then I'll from there derive what the optimal flexible protocol is. Right, so very quick recap of stream-led. You have some epochs, units of time running. Replicas do certain actions, right? So leader proposes a new block every epoch, and the new block extends a chain that has a quorum of 2/3 votes, right? So like the protocol may be a little detailed, but I want you to only focus on the things that are highlighted in the bold, which is here the 2/3 votes, right? Similarly, replicas vote on blocks, and they vote for blocks only if the previous chain is has, again, the Q equals 2/3 votes. And then there's also a confirmation. Note that this is done by the clients. When the client sees a certain number of consecutive blocks, like 3 consecutive blocks with 2/3 votes, then the client confirms the second one of them. That's the rule. And again, note the important thing here is the 2/3 votes. Right. So as I said, like if we want different clients to be able to confirm with higher safety, the very simple idea seems to be that, what if I wait for more number of votes? What if I wait for all replicas to vote on this block and then only I confirm? Then I should get more safety, less liveness, right? And that's the idea. That's essentially what the FBFT protocol is. I replace the confirmation rule, highlighted in blue now. Instead of the 2/3 votes, I wait for QK votes, which is a different parameter for each client, right? And so now if you look at this chain, a client that uses the 2/3 quorum will confirm this part, right? Because there are these 3 consecutive blocks with 2/3 votes, and I can confirm the second one. But there's another client who waits for a quorum of 1. 1 means like 100%, right? So this client only confirms up to here. And so that fits our intuition that for more safety, this client is waiting a little more, so less liveness. But I mentioned before that this only achieves a certain part of the trade-off, right? And why is this so? So let's look at, in particular, this client which confirms with a 100% quorum. And why does it only get safety up to 2/3? Right, so let's start with this scenario where there are these 3 blocks with votes from every single replica. And so this client is able to confirm this with its quorum of 1, like 100%. Okay. Now, suppose there's an adversary that has more than 2/3 of the replicas. then this adversary is able to create a new chain by itself, right? It can put all the votes on this other chain. And now what happens is that it can sort of coerce the other honest replicas to continue voting on its chain, right? Because the voting rule there only says that you can vote on something if there are already 2/3 votes, and it satisfies that, right? And so because of this, what happens, you end up with two different chains. Both have like basically every replica voting on them, and this is a safety violation because these two different clients have confirmed two different chains. And so we want to figure out a way to avoid this, right? And so the way we can see the problem that sort of happened is that honest replicas first voted here, but then the adversary somehow forced honest replicas to again vote on this new chain. And we want to somehow prevent this, right? And so that motivates, in some sense, the ingredients we need for the optimal flexible version. The proposal part remains the same, but I add another feature called a permanent lock. So notice the bold things here. So on seeing these three adjacent blocks, let me show an example, right? Okay, on seeing these three adjacent blocks with 2/3 votes, and it must be extending my previous permalock, then what I do is I go and permalock the second out of these three blocks. This is done by the replica, right? And then I add a rule that says that this replica will vote for a block only if it extends the replica's permalock, right? So that means if there is a block here, this replica will vote because it extends the permalock. But if there's a block here, this replica will not vote because it does not extend the permalock. And that's sort of the key ingredient here, really. And the third step here is for confirmation, I change from 3 adjacent blocks to 4 adjacent blocks. So, the rationale for this is as follows. Okay, so I added this permalock to say that honest replicas will not vote for 2 conflicting chains. But how does anyone who's looking at this chain know when someone has permalocked on this, right? So because of the fact that honest replicas permalock, I know it can be safe, but I don't know when the honest replicas will permalock. And for that purpose, I add another round of voting. The idea is that if I see that a replica voted for block D, then I know that it has also permalocked on B for sure. How much time do I have? Okay. Yeah, so these are the 3 key ingredients. And now we can see how this resolves the problem. And we can consider the same client who confirms with 100% quorum and see that it will now have safety up to 100% adversary and not just 2/3. And how does this work is, okay, let's start from the confirmation rule, right? You see 4 adjacent blocks with 100% votes. And that is what leads this client to confirm block B here in this figure. And as I said, when the client sees these set of 4 blocks, it knows that any honest replica that has voted for block D here, this honest replica has also permalocked B, because if it has voted, then it has also seen the previous all the previous votes on this chain. And basically, it's because of this that the client can be sure now that even if the adversary cooks up a different chain, this honest replica will never vote on the other chain, because it knows for sure that the client knows that this replica has permalocked the first chain. And so basically, no matter how powerful the adversary is, unless it has corrupted basically the entire set of replicas, there's no way you can get a full quorum of replicas on a conflicting block here. And so there will not be a safety violation in this. And so you can think of it as, yeah, effectively, I eliminate the safety violation by waiting for 100% quorum and using this permalock. Right, so to quickly recap this construction, the 3 key takeaways from this construction is that there's this permalock, which avoids contributing to conflicting confirmations. There is sort of an additional round of voting the 3 changed to 4 here, which we call as post-vote in the paper. And the role of this additional round is to inform the clients that the replica has done the perma-lock. And then, of course, there's each client using different fraction of votes for confirmation. Right, so these 3 ingredients: post-vote, the additional voting, perma-lock, and the confirmation rule, the flexible quorums. Notice that the first 2 are things done by the replicas. So it's sort of a system-wide configuration. Every replica has to follow that. And the last one is local decision by the client. So it can do that independent of the other clients. In the paper, we actually explain a generic construction where we can add these 3 ingredients on top of any existing protocol with 1/3 safety and liveness. And this sort of provides A, a generic, and B, a very conceptually easy understanding of this. But then what I described to you now in this talk was this generic construction as adapted to Streamlit, where basically we reused votes of the protocol. So you don't need to send any additional messages. So notice that the protocol I described does not send any more messages than the original Streamlit. So there is no zero communication overhead because of this. And sort of the most exciting part of this research I found was, even though the first 2 rows here suggest that there are some system-wide changes I need to make to the protocol, but it turns out that implementations of protocol actually have this something that's similar to what we need for the perma-lock. So Ethereum validators basically have a performance optimization where they try to save memory by forgetting about chains that are not on the finalized chain. And effectively, what that leads to is you don't vote on a chain that conflicts with what was once finalized. And that is basically giving us what we need for the perma-lock. And so the nice thing about this is that you can implement optimal flexible clients on Ethereum without having to do any system-wide changes. And so basically, clients can locally implement the rule. And we, in fact, provide an implementation and run this on the Ethereum main chain. I'll give you a very quick taste of what the experimental results look like. So if you were to confirm blocks using Ethereum's finality rule, it already takes about 16 minutes to do so. And now if instead of using the finality, you use like a higher quorum. So notice that the higher latency here is due to 2 reasons. One is I wait for an additional round of votes, and because I wait for a larger quorum. And so that leads to a slightly higher latency. But basically with like 6 extra minutes of latency, you can get all the way up to 100% safety in the worst case. And so in a practical sense, the trade-off becomes like, what's the worst case safety resilience versus how long you wait to confirm, right? And so if you, we saw how this rule behaves across time. The participation of validators fluctuates across time. Most of the time there are at least like 90% validators online, and so even the high quorums proceed pretty quickly. But in some instances, like during a hard fork, it takes time for all validators to participate in the hard fork. And during that time, there may be an interval of a few hours where sort of the high 99% quorums do not make progress, but they eventually catch up, right? That's the behavior we observe in practice. Yeah, that's all. I conclude the talk here. The details, like all the other safety proofs and more experimental details and results, are there in the paper on ePrint. And we also have the source code of the implementation for Ethereum on GitHub.
Right. So I have a question about this uninteresting triangle.
Good.
Okay.
It's there. Yeah.
So suppose I want to terminate when, say, I don't know, 40% of the replicas have crashed, but I'm okay with disagreeing if more than 1% of the replicas are Byzantine. Then I suppose I would fall into that uninteresting triangle. And is there anything we can do to accommodate me in this kind of consensus protocol?
Yeah, basically, okay, so your question is, you may believe that there are only crash faults, but not so many Byzantine faults, and that's why you
As
might
many,
want
yeah.
to confirm, even if, let's say, yeah, 40% have crashed. That's a good question. In that sense, in that case, you would lose security against Byzantine adversaries.
So
There are
yeah.
protocols that can do this. In fact, we also have a construction in mind which can do this, which can allow you to get even trade-offs in this region. But those constructions were not super efficient. And indeed, it's somewhat interesting maybe to look at constructions that can achieve that in an efficient manner.
I have a question.
Okay.
So it kind of looks to me that maybe this is like kind of the far end of the spectrum of maybe the fully asymmetric model, where you only allow some asymmetricity at the edges, right? And so maybe some of those insights are actually portable to more asymmetric configurations, where you push some of the asymmetry also inside the core of the network where you have the replicas. I don't know if you've thought about that.
Definitely, like, yeah, the techniques could apply to doing like a fully asymmetric setting where even the replicas have different trust assumptions. I think we approach this from the angle of like, the way it's stated now, it makes it more compatible to proof of stake blockchains, for instance, where the blockchain is already running with a threshold quorum and you want to add trust assumptions on, like, variable trust assumptions on top of that. But definitely one could use these techniques to for the fully asymmetric setting, and I think that's something we are looking at for future.
There's actually another difference. The model here is hybrid because we're separating safety from
Yes.
liveness concerns, right? It's yet another orthogonal dimension compared to the crashes versus Byzantine separation that Isaac just brought up, right? So we have a difference because if we're in the asymmetric model, otherwise there is just this one point where there is one set of failures, and we want to be safe and live in this set of failures. What happens here is the TS and the TF, or the TL and TS, TL, TS, the two dimensions, they only come up because we're separating the safety from the liveness, yeah?
Yeah, but in some sense, in the asymmetric model, you specify liveness by assuming just through a fail-prone set, and then your safety guarantee comes from intersection with others, right?
So in that sense, yeah, the generalization of this model would be that each client has not just like two numbers here, liveness and safety resilience, but it trusts that there is a certain set of parties who might try to break my liveness because maybe they're prone to crash. Maybe there's a certain set of parties that are out to break my safety because they are not trustworthy. And so these two things become like, there's a liveness failure prone set and a safety failure prone set, if you will. That could be an extension of this.
I see.
That's what you're getting to, I guess. Okay. Yeah.
Okay, interesting.